Hello, and welcome to Symbolic Logic, Unit 8, Introduction to Natural Deduction and the Concept of a Formal Rule. So here's a little recap and a little bit about our plan for today. So recently we've been investigating using truth tables to discuss and uncover logical relations between sentences. Today we'll continue this investigation, discussing some theoretical aspects of sentential logic. In the latter part of class, we'll also begin introducing a natural deduction system for SL. And this is going to be the main deduction system that we use for the remainder of this term. We'll talk about why this is natural. Essentially, the idea is that the system is intended to, in some ways, model careful human reasoning. It'll capture inferential reasoning through a series of introduction and elimination rules, and we'll spend some time today talking about what those are. First, to get a sense of the kinds of rules that we're going to be using and to get a sense of how natural deduction is going to function, we want to think about logical and non-logical symbols in arguments. So we can draw a distinction between these two things. So just consider the following formal argument. A and B, if A, then C. And the conclusion of this argument is C. And this is clearly a valid argument. But notice that this argument consists of two kinds of symbols. So first of all, there are the logical symbols, conjunction, conditional, therefore, and then there are also non-logical symbols. And here the non-logical symbols are A, B, and C. Notice that the meaning of the logical symbols is defined by symbolic logic or by sentential logic, and it remains static across all of our arguments, right? We know if that ampersand symbol, the and symbol, appears in a different argument than this one, it's going to mean the same thing that it does in this argument. Similarly, the conditional symbol is going to mean an if-then statement in every argument it appears in. It's never going to change its meaning. But the meaning of our non-logical symbols, such as these sentence letters, can vary. So that's why we need a symbolization key. So in this argument, right, these letters may stand for the following. If this argument may say, pizza is tasty and pizza is inexpensive. If pizza is tasty, then pizza is what's for dinner. Therefore, pizza is what's for dinner, right? So in this particular instantiation of this argument, that is the meaning of the sentence letters. But those sentence letters can change their meaning across different sentences. So for example, A may mean Phyllis is furry, B, Phyllis has 4 legs, and C, Phyllis is a pet, right? So in a different argument, A, B, and C could mean something different, but conjunction, conditional, therefore, and all of our other logical connectives and logical symbols are never going to change their meaning across arguments. Okay, so we have logical and non-logical symbols. And we might think, first of all, well, how do we know that what the meaning of a logical symbol is? How do we know if that logical symbol stands for a sentence? How do we know whether that thing is true or false? Okay, so we have logical symbols and non-logical symbols. And so far, the non-logical symbols we've talked about are sentence letters. And sentence letters are going to stand for, oftentimes, atomic sentences. And now we can think about the atomic sentences. How do we know if an atomic sentence is true or false? So consider this atomic sentence, M. And now I ask you, is M true or false? Well, we can't tell, obviously. And so the question is, what do we need in order to know whether or not M is true? And so it seems clear that one thing we need is an interpretation or a model. An interpretation or a model is just what's going to tell us what M stands for. So you might think of it as a symbolization key specifying the meaning of M. Now, if we have such a symbolization key, we'll be in a better position to tell whether or not M is true. So suppose this is the interpretation, the symbolization key for M. M stands for the moon orbits the Earth. Well, now we can ask ourselves, okay, we have an interpretation for M. We know that what M stands for. It stands for the sentence, the moon orbits Earth. And now we can ask ourselves, is M true or false? And it seems here that the answer is 1, M is true, right? So on the interpretation where M stands for the moon orbits Earth, we know it's true. But M could have a different meaning. Instead, M could mean the moon is a giant turnip. And so what if M stood for the moon is a giant turnip? Well, then would it be true or false? Well, the answer is in that case, M would be false, right? So clearly we need an interpretation. We need something that tells us what M stands for to understand its truth value, to understand whether or not it is true or false. But notice that's not all we need, because even with this interpretation, the moon is a giant turnip, we could in some instances get a different truth value, right? We also need a state of the world, a universe, or a domain of discourse to tell us whether or not this sentence, M, is true or false. We thought that the moon is a giant turnip was false because the state of the world, or the universe, or the domain of discourse, the things we're talking about, in our world, in our universe, this statement is false. The moon is not a giant turnip. But we can change the truth value of M without changing its interpretation if we change the world. So, right, what if the moon were actually a giant turnip? Well, then in that case, this sentence would be true, right? We haven't changed the interpretation of M, but we have changed its truth value by changing the world, right? So for any sentence, for any atomic sentence, whether it's true or false, we need an interpretation plus a state of the world. And those give us the truth or the falsity of an atomic sentence, okay? So an atomic sentence's truth value is relative to its interpretation plus the state of the world. And this is important to bear in mind. Okay, notice that interpretations and models allow us to determine the truth value of atomic sentences by telling us what they mean. We can use this then to determine if they're true or not by looking at the way the world is. But the truth of sentences involving logical symbols or connectives is a function from the truth value of the atomic sentences that compose them. It isn't simply given to us by an interpretation or model, right? So we can see this by supposing that we have a truth value assignment. I'm going to call it alpha for assignment, that tells us the truth value of all the atomic sentences in a given model relative to a world, right? So you can imagine that this model, it's an abstraction, an idealization, but suppose that it just tells us the truth value of all the atomic sentences in a given model relative to a world, right? So we know what these sentences mean, and now it's just going to tell us this one's true, this one's false, this one's true, this one's false, right? In other words, you might suppose that A assigns a truth value to any atomic sentence of SL, and we can call that atomic sentence P, that we happen to use. So it gives the following values. Since we're in a bimodal logic, it's going to give 1 if the sentence is true and 0 if it is false. And so you can just imagine that you have a list of all the sentences, all the atomic sentences, and A is just going to give us true, true, false, true, true, false, 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 true, false, 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 for all of these sentences, right? So we get all the values for all of the sentences relative to the state of the world that's of interest to us, right? So what A does is it assigns a truth value of 1 to P if it is true, and 0 otherwise. Okay, so we have now a list of all of the truth values for all of the atomic sentences. But of course, we don't only have to speak in atomic sentences. We can also speak in complex sentences. So how do we move from having this list of all the truth values for the atomic sentences to this more inclusive list of all possible sentences that we might want to speak? And so the idea is that function V, V for value here, is going to tell us, is going to be a function that moves from A, an assignment of truth values to each atomic sentence, to a truth value to every complex sentence of SL, right? So supposing we know what the truth values of atomic sentences are, then we can use V, function V, to move from those things to discover every possible true sentence in our world. So the idea is that this function is going to consist in a series of conjoined conditional statements. So in effect, it asks, what is the formal structure of a given sentence? Then it tells us its truth value dependent upon the truth values of the atomic sentences which compose it, right? So if you have a certain formal structure for a complex sentence, then you can just plug in the truth values for the atomic sentences that make up that complex sentence, and V will tell you what the truth value of that huge complex sentence is. Okay, so here's how function V operates. So suppose first that phi is a sentence letter. Then the value of phi equals a phi or alpha phi, okay? So whatever the truth value of that atomic sentence is as specified by alpha, that is the truth value after the function has done its business. So if phi is a sentence letter, then the truth value of it simply is the same as the alpha value of that sentence. Now, suppose that phi is negation psi for some sentence psi, right? So again, phi is a variable we're using to talk about a sentence. And suppose the sentence we're talking about is negation psi, where psi is a different variable to stand for some sentence that has a value that is an atomic value, sorry, that is an atomic sentence and has a value under alpha. Well then, the value for phi, again, negation psi, is 1 if the value of psi is 0 according to alpha, and it's 0 otherwise, right? So if whatever sentence is symbolized by psi is false according to alpha, which assigns values to atomic sentences, then the value of psi here, the value of phi here, this thing, is going to be 0, is going to be 1 if the value of psi was 0 in alpha. And otherwise, the value of phi will be 0. Now, what if phi stands for the complex sentence psi and omega? For some sentences, psi and omega, whatever those sentences are, then the value of phi will be 1 if the value of psi is 1 and the value of omega is 1, and otherwise it will be 0, right? So if we have a conjunction of psi and omega, and we've conjoined those things, and we know it can only be true if each of the conjuncts are true. So the value of psi, which is the abbreviation again for, the value of phi, which is the abbreviation again for psi and omega, is going to be 1 if the value of psi is 1 and the value of omega is 1. Otherwise, it's going to be 0. Moving ahead, if psi is the following sentence, if phi is the following sentence, psi or omega, for some sentences psi and omega, then the value of phi is 0 if the value of psi is 0 and the value of omega is 0, but otherwise it's 1. Right? So this just expresses our disjunction rule. If we have a disjunction of two sentences, it's true so long as one of the disjuncts is true. It's false, it gets 0 if both of the disjuncts are false. We can express a rule for conditional or a function for conditional. So if our sentence phi is a conditional statement, if psi then omega, for some sentences psi and omega, then the value of phi will be 0 if the value of psi is 1 and the value of omega is 0. And it'll be 1 otherwise, right? So either the consequent is true or the antecedent is false, right? So that gives us our function to work from atomic sentence values to the truth or falsity of if psi then omega, which is our sentence we're interested in here, or phi. And then finally, if phi is psi if and only if omega, for some sentences psi and omega, then the value of phi will be 1 so long as the value of psi equals the value of omega, and it will be 0 otherwise. So this function, function v, gives us a way of working from this kind of abstract ideal notion, alpha, which gave us the truth value for all of the atomic sentences we might want to talk about. Function v can give us the truth value of every sentence we can say in sentential logic from the truth values of those atomic sentences. So if we have the truth values of the atomic sentences, then we can use v to get to the truth value of any sentence whatsoever. So what does this give us? Well, let's take a moment to appreciate what it gives us. So again, suppose A is a finite assignment of truth values to a limited set of atomic sentences describing the world, right? So suppose it's, a set of sentences that are of interest to us and we know the truth value of those atomic sentences. Then the semantics of SL gives us an infinite set of sentences through the recursive combination of the limited set of atomic sentences and logical connectives. In other words, even if we just have this finite set of atomic sentences, alpha, and we know their value, we can use sentential logic to construct an infinite set of sentences from that, and we can know those sentences' truth values as well. It gives us a way to determine which of those sentences are true to the extent that we know the values of alpha. Another way to put point 2 is that V shows us the entailment relations that exist as a result of the logical connectives of SL, right? So it tells us what will be true, what we can infer based upon a limited set of atomic sentences from the connectives of SL. And this is huge. And so I think an important thing to notice here is that the basic idea of this function from atomic sentences to complex sentences, function from alpha to V, allows us to see formal rules, and these are rules that will maintain the truth value of our starting premises. So recall this functional rule. This is number 4 from V above. So it said if phi is psi or omega, for some sentences psi or omega, then the value of phi equals 0 if the value of psi equals 0 and the value of omega equals 0. But otherwise, the value of phi equals 1. Okay, so this tells us that if we have this sentence, phi or omega, we know that that thing's going to be true so long as at least one of psi and omega is true, right? And so we can use this functional rule to infer certain true conclusions from a premise. So it supports a number of inferences, in other words. So for example, suppose that the value of A equals 1, right? So suppose we just have an atomic sentence an atomic sentence A, and we know that the value of A equals 1, right? Or we could say A is given the value of 1 under alpha too. We can change that to an alpha A. Suppose that it tells us the value of A is 1. Then we know that the value of A or B is going to be 1. And that's according to this claim, to this functional rule, right? Which tells us so long as one of the disjuncts is true, then the disjunct as a whole is true. So we can infer the truth of A or B from the truth of A. So if you give me the atomic sentence A, I can say, well, I know that A or B, right? If you tell me A is true, then I can say, well, I know A or B is true, regardless of the meaning of A or B. It doesn't matter. So I can infer something true from a true atomic sentence, right? If I have the atomic sentence A, then I can infer A or B for whatever value B is to be true as well, okay? So this tells us, and it tells us simply by thinking about this functional rule, that if we're presented with a true sentence, we can derive a true disjunction from that sentence by just disjoining any other sentence to that thing. Similarly, if the value of A is 0, but we know that the value of A or B equals 1, then it's a small step to infer that the value of B equals 1, right? Rule 4 from V told us that the only way a disjunction can be false is if both of the disjuncts are false. So if we know a disjunction is true and we know one of the disjuncts is false, then we are in a position to infer that the other disjunct is true, okay? So as we can see, our system V, our function V, allows us a lot of inferential power. We can infer new true sentences from what we know about our existing sentences. And these two steps, which we can see are supported by V, by function V, they capture two of the formal rules of the system of natural deduction that we will be developing moving forward. So why natural deduction? Well, this system, the system of natural deduction that we're going to be developing, is intended to do a few things. First, it's intended to model human reasoning in a closer way than some methods we've looked at previously, particularly the truth table method. And it does this by illustrating the connections between various claims, by illustrating the way in which we're in a position to infer new information from old information. Additionally, this system of natural deduction shows how and why an argument is valid, right? Our truth table method could tell us if an argument is valid, but it didn't tell us anything about why it's valid or not. We just would see, for example, that there's no way for the premises to be true while the conclusion is false, just given the logical structure. But we don't really know what the machinery is there that is grounding that truthful inference. So this system is an improvement on that because it's going to give us additional information about why an argument is valid. That's not always the best method for showing that an argument is invalid. Counterexamples will continue to remain an important role, an important feature that we need to investigate invalidity. And then finally, this system provides certain advantages over the truth table method for assessing validity and other logical notions. Importantly, natural deduction proofs tend to be shorter than many truth tables. So if you think about it, the number of rows we need for a truth table grows exponentially the more sentences that we add in, the more atomic sentences that we add in. Already with 4 atomic sentences, we're up to 16 lines of a truth table. With 5 sentences, we get up to 32. So it's just that our truth tables grow exponentially, and that's problematic. It can make it difficult for us to deal with arguments involving more than just a few atomic sentences. Natural deduction doesn't have this problem. Additionally, because the truth table method, while purely mechanical, was very labor intensive, it could lead to us making mistakes about when an inference was actually valid from some other inferences, and that can lead to all sorts of problems. natural deduction, in not requiring so many ticks and talks and tracking how things are going in different places in this big complex matrix, makes it actually easier for us to avoid making simple mistakes, I think. So those are some advantages that natural deduction has over the truth table method. So let's think about our old method, truth tables. So there's a benefit to these because they can prove tautological consequence, tautological equivalence, tautology and contradiction, and many other notions. But there are many drawbacks. So again, as I've just said, they require more rows the more atomic sentences we have. So, right, if we had 6, it would require 64. If we had 7, it would require 128. Additionally, they require a lot of columns with more premises, so they can be longer than a sheet of paper. And because there are so many rows and columns, as I've just said, it can lead to simple mistakes. And then finally, truth tables don't really resemble informal reasoning principles. They're more like something a computer would do to solve a problem, and they lack that kind of human touch to them that we really want in our methods of argumentation. So our new method is called formal proof or natural deduction. And so what we do with formal proofs is we start with the premises of an argument, and we apply rules that preserve the truth value of different inferences that we draw. In other words, if we're starting from some premises supposed to be true, then our rules, which are grounded in V, our function from simple sentences to complex sentences, our function from the truth values of simple sentences to truth values of complex sentences. If we start with true premises and apply rules that preserve truth, that will only allow us to derive true conclusions from those true premises, to arrive at the conclusion by applying the rules step by step, then we should have a way of drawing deductively valid conclusions from a set of premises. So the idea is that there are truth-preserving rules for each connective and for identity, which will be introduced later. Additionally, there are truth-preserving rules for our quantifiers, which will also be introduced later. So that would be the universal quantifier and the existential quantifier. And we'll talk about those two later in the term. So in getting this method going, it's important first to pay attention to the setup of the method. So again, as we've gone over before, you need a Fitch bar. And that is just a bar that is going to serve as the starting point for writing out your premises. So your premises will go just to the right of the bar. And then the line, the horizontal line is going to tell us where the premises end, right? So all of your premises go above that bar, and then below that bar, you are going to get the steps of the argument, right? So you're going to get the premises, premise 1, premise 2, however many premises are given to you in the argument. And then you're going to write additional steps in between those premises and the conclusion. And you stop when you've used the rules that we're going to develop to generate the conclusion. Okay, so what do our formal rules look like? So the formal rules, again, are what we are going to use to derive additional steps from initial premises and other additional steps as we construct proofs, right? So we're going to use formal rules to move from our premises, other additional steps derived from those premises, to more steps in our proof, and then ultimately to deriving the conclusion. These are called formal rules because they ground valid inferences from sentences of one form to sentences of another form, right? So they don't really care about the meaning of the sentence, but if we're presented with sentences that are true, then we can use these formal rules to derive additional information, additional true steps along the way. Additionally, these rules are truth-preserving. And so, as I mentioned before, the idea here is that, like the previous kind of considerations based on V, they'll allow us always to derive all and only true inferences from our initial premises, right? So we know the truth values of our initial premises. We know our initial premises are true. Then by applying these rules, we will always arrive at things that are true. We'll never end up somewhere false as long as we're applying the rules appropriately to premises that are true. And so for each of our connectives, and again, we have 5 connectives. Those are negation, conjunction, disjunction, conditional, and biconditional. So for each of these connectives, for each of these connectives, we're going to introduce an introduction and an elimination rule for that connective. So the introduction rule is going to be a rule that allows us to move to a sentence involving that connective, right? So if we have the introduction rule for disjunction, then we're going to introduce a disjunctive sentence that we didn't have before. Elimination rules, on the other hand, are going to allow us to move away from that connective. So we might move from a disjunction to the truth of one of its disjuncts using an elimination rule, for example. So for each of our connectives, we're going to have 1 introduction rule and 1 elimination rule. So for the connectives of SL, you will be learning 10 rules and using these to derive, to naturally deduce conclusions from premises. Next time, we're going to spend some time looking at some initial formal rules for conjunction and disjunction. All right, that's it for today. Bye.